Well, yes, a couple of thanks. So first, I would like to thank Yuri for being born about 85 years ago and being the raison d'etre for this very enjoyable event. And then I would also like to thank Guillermo for the kind invitation and the opportunity to give this talk here. So, of course, this talk is dedicated to Yuri on this occasion, but I want to emphasize that this is not just a courtesy dedication, because in fact, my fascination with this topic of zero-one laws started about 30 years ago when I read this wonderfully written article column by Yuri in the bulletin of the EATCS. And still much of what I know on the topic comes from this article, so highly recommended. All right, now my talk will consist of two parts, and the first one will be kind of give you a background, a brief overview of zero-one laws in classical logic and some extensions, but then I'll also mention some failures of zero-one law. And in fact, let me say this. So I started doing some work in this area some 25 years ago, trying to reprove, to find a new proof of a zero-one law for model logic that was result published by Halpern and Capron. But, well, it was, so the proof was not understandable by model logicians, so that I wanted to find another proof that was understandable by model logicians. And I failed on that. Instead, I actually essentially disproved that result, but I will not go into that story. So after I failed with this, then I changed my focus, namely from zero-one laws to the question of characterizing almost sure truths or almost sure validities of structures in various logics. And so this would be the main part of my talk. I hope I will get to say enough on this. Right, so, all right, let me start with some background. Now, consider any fixed finite relational signature. You can think of graphs or directed graphs as if you prefer. Then we can talk about, so for any natural number n, we can talk about a random n-element structure for this signature. And we can do it in two different ways. So one is if we consider the domain of the structure fixed, like, well, the elements are the numbers from 1 to n, and then we define the structure on top. So this will be the labeled version. And the alternative would be to consider the structure up to isomorphism. So that will be the unlabeled version. And for each of the two, we can then define the probability space, and we can assume uniform distribution now for simplicity. So, well, in either case, we'll have finitely many elements of this space. All right, so this is for every fixed n. Well, then we can respectively talk about labeled and unlabeled probability for a given property of structures to hold on a randomly chosen such structure of n elements. So for every n, we have these two probabilities, and they are classical probabilities. And then next step is let n tend to infinity and see what happens. And so, well, if this probability as n tends to infinity has a limit, then this would be denoted that way there, and likewise for the unlabeled case. And so if these limits exist, then we can talk about asymptotic probabilities of labeled and unlabeled asymptotic probabilities of this property to hold. Okay. So for now, I will focus on the labeled case, and you will see why. By the way, notice that this so-called probability measure is not countably additive, so that we call it probability. So now, the key definitions. We say that a property is almost surely true, or valid if you prefer, in the finite if this asymptotic probability is 1, and it is almost surely false or invalid in the finite if it is 0. All right. So, well, some terminology that I'll be using later. So take a binary relational structure, just one binary relation, and hereafter I'll call it a frame. So this terminology comes from model logic, not so important. So that in this sense, a directed graph, a digraph, is a loopless frame. Whereas a graph, that is undirected graph, is a digraph with a symmetric edge relation. So I will use this terminology consistently further. Now, to give you some examples, first of almost surely true properties of graphs, and most of them also apply to digraphs. For instance, connectedness, well, having a k-clique, being Hamiltonian, and so on, are some examples. But also an important example is rigidity. So graph is rigid if it has no non-trivial automorphisms. And because rigidity is almost surely true property, that implies that the labeled and the unlabeled case will lead to the same probability, because we always factor, well, with probability 1, the same number. So some examples of almost surely false properties would include, for instance, on graphs being planar, being k-covariable, Eulerian, tree-like, and so on. On directed graphs, for instance, well, the edge relation to be symmetric or transitive for any non-trivial universal property would be almost surely false. Not very difficult to see why. So in particular, by the way, and this is essential for what will follow, is that a randomly chosen frame is almost surely not a digraph. And a randomly chosen digraph is almost surely not a graph. So that one should not expect necessarily transfer of such asymptotic probabilities going from one to the other. Okay, now, next. So here is a mental experiment. Take a countable set, like the copy of the natural numbers, and then for every pair of natural numbers, different natural numbers, toss a coin. It may be fair or biased coin, doesn't really matter. Toss a coin, and then if it ends up heads on, then cast an edge between M and N, that is, declare that M and N are related, and otherwise not. Okay? And so you do that, well, mentally for every pair of different natural numbers. And so the result would be what we can call a random countable graph, randomly constructed countable graph. Now, suppose you do this experiment twice, so two different people do it simultaneously. What do you expect would be the chances, the probability that you end up with two isomorphic results? So those who don't know the answer, would you like anyone to take a guess? Or you all know the answer? Preaching to the converted. Okay, well then you know the answer. The answer is 1, probability is 1, and the reason is that there is this very special countable graph which goes under various names, Erdős-Renyi graph or Rado graph and so on, such that any randomly chosen or constructed countable graph is isomorphic to this one with probability 1. Okay. And so, in fact, there is a very nice and simple logical characterization of this graph, and it is based on these so-called extension axioms, which, is there anyone who has not seen the extension axioms then? Okay, well then I explain what they are. So this is, all right, it's a first order sentence. What it says is if you take an n-tuple of vertices u1 to um, and an n-tuple of disjoint n-tuple of vertices v1 to vn, then there is a vertex w, which is different from all these, which is edge related to all the u's, and it is not related to any of the v's. So in a sense, this is some sort of saturation property here. Okay. And so, well, there are infinitely many sentences like this, and they will play an important role, as you will see, on what follows. And what follows is Geifmann's theorem, 1964, when Geifmann proved that a countable graph G satisfies all these extension axioms precisely when it is isomorphic to R. And so, in fact, the proof sketch is kind of a very natural generalization of Cantor's Cantor's characterization of the order of rationals, so it's a back and forth argument and not go in details. But as an important corollary, the theory that is axiomatized with our extension axioms, it's omega categorical, and of course it has no finite models, and therefore it must be complete. And so these extension axioms, they generalize in a natural way to any relational language signature, so that we can talk about a countable random structure of any such signature. Okay, so, well, in particular, we can do that for graphs and digraphs and frames and so on. And now, Pagin comes into the picture. 1975, he proves that every extension axiom is almost surely true in the finite. And the proof is kind of a fair combinatorial probabilistic exercise there. I'll not go into this. But then, so using this lemma, he proves this very to me, beautiful theorem. It says that for every sentence of our language, the following are equivalent. That sentence is true in the countable random structure graph precisely when it follows from the extension axioms, and it's precisely when it is almost surely true in the finite. In other words, the almost sure truth in the finite turns out to be equivalent to a precise, crisp truth in one particular infinite structure. So this is the transfer theorem. And then as an immediate corollary, because every such sentence is either true or false there, and if it's false, then its negation is true, then what follows is that every first-order sentence will have an asymptotic probability, either 1 or 0. And so this is essentially the 0-1 law. And well, to state it in a few more words, every first-order property of a relational structure is either almost surely true, almost surely false in the finite. So, by the way, that result was, well, the first result of this type was proved already by Carnap in the 1940s, but it was for a very simple case, the monadic first-order language. But it was also proved earlier on by the Russian mathematician Glebsky and his students listed there in 1969 in the general case. And the proof was based on a kind of almost sure quantifier elimination, but it was published in a local Russian journal, and it was apparently inaccessible to Fagin when was it, before or after Fagin's? Ah, right, okay, but so at least as far as I know, Fagin was not aware of this result when he proved his. So. Well, maybe you know more, you know some dark secrets here, but in any case, whether he was aware or not, but I find Fagin's argument much more illuminating, and I'll say more why. But to give some, due to this approach on almost sure quantifier elimination, it was actually proved, used a bit later by Etienne over there. Am I right, Etienne, that you use this almost sure quantifier elimination to prove the complexity of almost sure truth? Or you don't remember? Right, because, yes. So anyway, this is really a very interesting, I mean, it's a remarkable result because, of course, we know that, validity in the finite and first-order sentence is undecidable. Well, this is Trachtenberg's theorem. And so there is kind of a deep philosophical message here that if you want to settle for almost sure validity, not precise, but almost sure validity, then all of a sudden you live in a much simpler world. So there is something to say here. By the way, now, when I was preparing these slides, and I thought that, well, maybe then I should say something about the decidability of the monadic second-order theory of this countable random graph. And I believe that I had the answer to this, to the question whether it is decidable, but I could not recall a reference. So sure enough, I Googled it. And so, well, you can see my query on top there. And there, Google gave me an answer. Yes. And, well, it went on explaining, actually. And interestingly, so one of the main references there was one of the, or maybe more than one of the papers by Yuri and Shelah. So, okay, but I looked them up, and I did not actually find these proof there, so that I thought, okay, well, it's something missing here. So let me run this query again. And so I ran it again, and I just, because I was lazy, so I shortened this to MSO. And lo and behold, I got another answer for the same query. You see that Google recognized that it's the same query. Got another answer, which is even funnier, is that one of the references there was again to one of Yuri's works. So apparently Yuri proved everything that is to be proved out there. By the way, so that also tells you that this Google's program is, well, in terms of Lifshitz definition, it is not equivalent to itself. So anyway, this is so much about, asking Google technical questions. You won't. But back to the story. So that was all. I so far mentioned the 0-1 law for first-order logic, but let me also mention what happens when you look at some variations or extensions. So first, if you want to relativize, not to the quasi-false structures of the language, but some interesting natural subclass, what happens then? Well, in general, it is not known. And apparently, this is a very difficult question, but there are some particular cases that are known, and I very briefly mention them here. For instance, well, for simplicial complexes, there was no paper by Blas and Harari, partial orderings, the class of click-free graphs, and so on. Now, there are also some very interesting, nice results on zero-one laws for some essential extensions of first-order logic, starting with a work by Taranov, so it was one of the students of Glebsky, for the extension with a transitive closure operator. That was later subsumed and strengthened by a very nice paper by Blaskurevich and Kozen for the extension of first-order logic with fixed-point operators, which was even later then strengthened by result by Koitis and Vardi on the infinitary logic. So that's so far so good. It looks like, well, the zero-one law rules. Right. By the way, all these results were based on variations of Pagin's transfer theorem. So they were based on transfer theorem. This is important. Okay. Now, well, so lest you start feeling that or thinking that zero-one law always holds, that is, of course, not the case. It's very easy to, in fact, to invalidate it. It suffices to just put one constant symbol and one unary predicate in the language, and then obviously you don't have a zero-one law because the probability for this to hold would be a half. Right. But still, Lynch proved that if you have unary functions, then every first-order property would still have an asymptotic probability, not necessarily zero-one. Then it is also very easy to fail it in second-order logic or even in the existential fragment. For as long as you can define evenness there, then you can see how this can fail. But also the transfer theorem fails there easily too. So for instance, well, this is an example. There is a linear order with no maximal element. Well, that is false in the finite, but true in the infinite. So, well, anyway, there was a sequence of sharper and stronger results on failures of zero-one law in fragments of monadic second-order logic, starting with Kaufman's results, failure of, in the existential monadic second-order with one binary relation. It was later strengthened by Labarthe, which was a colleague, and I believe a student of Etienne. Was he your student? Or you? Right, okay. And so he really mastered this art of designing counterexamples to fragments of MSO, and that was actually very useful for me because I used him as kind of a hired assassin to to do the final step of disproving the zero-one law for model logic. Anyway, these examples, Labarthe's examples, are based on versions of the notion of a kernel. So briefly, well, maybe I should ask anyone who does not know what the kernel of a graph is. Everyone does? Okay, well, then it's easy. So I just display the definition. But what is important is that, so this is a property definable, of course, in monadic second-order logic, existential monadic second-order logic. And it was proved by Fernandez de la Vega that this property is almost surely true in the finite, both for graphs and digraphs. There is more to say here, but I will skip it because it's not part of my story. And so kernels will play an important role later on. But so for now, I mentioned them because Labarthe modified this notion of a kernel in various ways to prove, as I said, sharper and sharper counterexamples. And in particular, one of them that I mentioned here is very interesting because essentially, well, this property does not have an asymptotic probability because it kind of oscillates. And why it oscillates? Well, I will not say now, but ask me if you want in the Q&A. So anyway, now that was the brief overview of the first part of my talk, which took, of course, more time than I wanted. But I'll move to the second part now, which is focusing on the theory of almost sure validities in the finite in a given logic. So we fix the logical language, and then we consider finite models of this logic, and we define in this. Sorry, I denote in this way AS the set of all validities of that logic. The set of all sentences of that logic that are almost surely true in the finite. And so, well, if you look at this, you realize that this is actually a very well-behaved logical theory in a kind of traditional sense. It contains all validities of the logic, and it is closed under all finitary rules of inference. Right, so very nice. So here is the generic problem in the focus of this study. Find a purely logical, be it axiomatic or model theoretic characterization of this logic, of the almost sure validity. Now, there is a dichotomy here. There are two possible cases. One is the easy case, namely when there is this countable random structure there is a 0-1 law, there is a transfer theorem, and so then you have it all, like in first-order logic. But the other case is, well, what happens when there is no such a structure? Well, there is one, but there is no transfer theorem, or there is no 0-1 law at all. And for all that I know, it turns out that these cases are really, really difficult to answer. And so there are very, very few results that I know of 0-1 laws that are not based on transfer theorem, and none of them is trivial. So that generally, and describing this logic in the difficult case is a major challenge as far as I know, and in the remaining part of my time, I'm going to tell you a bit more about an approach that I've taken to try and face this challenge, and some observations and some conjectures. So by the way, I should say that this is not a mainstream topic of my research. So it's kind of a pet topic. It's a hobby topic, which I come back to when I have such nice occasions like this. And so it would be nice if I get a further push on this, if anyone wants to join. So that the ultimate, particularly this project, the ultimate goal is to describe the almost sure validities of MSO, or graphs or directed graphs. Okay. Now, so first some observations and some questions that naturally arise. To begin with, this is a useful observation by Curtis and Vardy that any universal MSO sentence is true in the countable random structure precisely when it follows from some extension axiom, and by compactness. It's a compactness. So this is useful because that tells us that every universal MSO sentence that is true in R is already in the almost sure theory, MSO theory in the finite. So that we have this very natural inclusion. All right. Now, respectively, by contraposition, every existential MSO sentence that is false in R is almost surely false in the finite. So that we have two results here. And now, natural questions that arise. First, is this inclusion proper or not? If we have an equality, then we are done. If the inclusion is proper, that is, if there are properties that are here, but they are not true in the countable random structure, then question is how to characterize such properties, and so on, and likewise for the MSO. So that, again, I will give you some partial answers and some conjectures here. All right. So, well, the approach that I'm taking here is based on the notion of a homomorphism, and I'll start with the standard notion, and then we'll see how far it traces, and the fact that, well, existence of homomorphisms can be described by EMSO sentences. So again, to remind you, a frame is just a binary relational structure, and well, for two frames, we define a homomorphism from one to the other as a mapping which preserves the relation. So it's a relation preserving mapping, as you would expect. Now, so now let us fix a finite frame like this one. Then ask the question: given a frame, another one, is there a homomorphism from that other frame to this target frame? And so, well, it is quite easy to see that, well, existence of such a homomorphism can actually be described, can be characterized by an existential MSO formula like this, which says there is a partition of the source frame such that so-and-so holds. This is a kernel partition of this homomorphism. So that we can characterize existence of a homomorphism from G to F with this EMSO formula being true in G. Okay. So that, again, we can talk about a kernel partition that corresponds to existence of such a homomorphism. And it's a kind of universal property, nothing to do with graphs specifically. Okay, so that existence of a kernel partition is determined by a fixed, which is determined by a fixed finite pattern, is characterized by such a sentence. And so that basically tells us that this is a natural class of potential EMSO properties that we might be interested in to characterize the almost sure probabilities. But how am I doing time-wise now? Okay, so doing fine, more or less. So respectively, non-existence of such homomorphisms of kernel partitions would provide a natural class of universal MSO properties. And so question is, how far can we get there? In other words, is this question whether such a homomorphism exists or not, is it really useful and interesting? So let's look into this. So again, we fix the target frame, and then we are asking the question whether randomly chosen frame would have a homomorphism onto this one, and how likely or not this is. So some easy answers or observations. If the target frame F has at least one loop there, a vertex with a loop, then the property is trivially true, because then everything you can map onto this loop. On the other hand, if F is a digraph that is loopless frame, then, well, this property that claims existence of homomorphism is almost surely false in the finite. And this is because existence of a loop is almost surely true, so that you cannot then map a loop onto a loopless curve. Then next observation is that the random graph, the countable random graph, has arbitrarily large cliques, and therefore there are no homomorphisms to finite graphs at all. So, okay, to wrap up, basically, it appears, it turns out that these properties of existence of or non-existence of homomorphisms, they are too weak to be of really of interest for us to capture interesting, non-trivial, almost surely true or false properties. And so that the idea then is, well, let us strengthen this notion of homomorphism. Let's make it a bit stronger and then see what happens. And so here is where a notion coming from model theory of model logic comes, and in fact, well, this is where I came from. It's the notion of a bounded morphism, also known as p-morphism, and so on. So I'm not going to go in much details, but this is a homomorphism that has this additional back and forth properties. So the fourth property says that if in the first frame there is an edge from x to y, and x gets mapped onto something in the second frame, then we can complete this kind of diagram. That is, there exists an edge from the image of x to some other element, which is an image of y. And the back property is likewise, but going from F2 to F1. So this is a stronger notion of homomorphism. And it turns out that very likely this is the right one that we need. I say very likely because there are still some conjectures there. But again, so we can characterize the existence of such bounded morphisms by suitable existential MSO properties, and you can figure them out. What is important is that for any given frame, it will satisfy this property precisely when there is a bounded morphism onto the target F. Okay, now I want to give two examples, and then I'll tell you why. First one is about a kernel. So the standard notion of a kernel that everyone apparently knows, it can actually be characterized by this target frame consisting of just these two vertices and a loop on X in the following sense. For almost every frame, almost every, that is with probability 1, every finite frame, I should say, because this is about finite frames, of course. We are interested in finite frames. So F will have a kernel precisely when there is a bounded morphism from F onto this one. And it's precisely when it satisfies this characteristic formula. Okay. And then the second example is similar, but now we have a more complicated story. So it's a 3-element target frame here, and it defines the notion of a double kernel. And so double kernel is just a kernel that consists of two kind of subkernels. And again, we have the same results, that for almost every finite frame, it has a double kernel, if and only if there is such a bounded morphism onto this one, if and only if it satisfies the characteristic property. So why are we interested in double kernels? Well, I'll tell you now why. So, but before I tell you, so a natural question now arises: can we characterize those finite frames for which there is a bounded morphism from the countable random frame onto this one? Bounded morphism. And so it turns out that the question is non-trivial, but it is not difficult either. Because the characterization is very simple, namely, these are the finite frames that have a central point. The central point, it's a vertex that can see and is seen from every vertex in the frame. Focal point. All right, so then there is this proposition that a finite frame has a central point if and only if it is a bounded morphic image of the countable random frame. And so this is a very simple natural characterization, and it gives us some useful consequences. That first, for every finite frame that does not have a central point, the existence of a kernel partition is almost surely false on the finite. And that is a universal MSO sentence, and in fact, it can be also defined in monoid. And the other corollary is that the countable random frame has all the kernel partitions that are defined by finite frames with central point. In particular, it has a single kernel and a double kernel and so on. Now we come to the question. So is the existence of such kernels, after all, almost surely true in the finite? Well, if there was a transfer theorem, which we hope and expect, then it ought to be the case that they are true in the countable random. And also here is the surprise that came to me. So basically this is the kind of eye-opening observation that I made some 25 years ago, published in this joint paper with Kaplan, that the existence of a double kernel is almost surely false in finite frames. And so the proof is, again, well, more or less following standard technique, but non-trivial, combinatorial analytic estimation of the expected number of double kernels and so on. So there are 3 slides with technical results that you can just glean, and if you want to ask me in the Q&A. But so again, there is nothing magic here. It's just doing the hard work, doing the. Sorry? Okay, good. So I'm doing well. So I'll be done on time. So we'll have enough time for questions. But anyway, so that's how the proof looks from a quick look. It's combinatorial probabilistic work. All right. So again, what is the upshot? What is the important consequence from this result? That we have a property that is true in the countable random frame, and it is, well, existential MSO property, but it is almost surely false in the finite. And so that means that there is no transfer theorem. There is no transfer theorem, and this is where the real story for me started. Okay, and now, so in the remaining few minutes, I want to give you a kind of a brief outline of the current state of affairs, which is mostly observations and conjectures, and I'll focus on the conjectures. So, but again, the agenda here is to obtain some sort of explicit characterization of the almost sure validities in the finite, in the universal, or the existential, or the full MSO on frames of graphs or digraphs by inspecting the possible kernel, sorry, the possible existences of bounded morphisms onto target frames and characterizing or classifying those that are almost surely false and almost surely true and possibly without asymptotic probability. And so this is the idea. And again, well, by virtue of what I presented earlier, we can focus on the set of all finite frames with central points. So that basically the question now boils down to some hardcore combinatorial probabilistic work to identify those finite frames with a central point for which there is almost surely a bounded morphism from any randomly chosen finite frame, and for those that there is almost surely no such a bounded morphism. And so I introduced this notation for part of that. And for all that I know, and I've done some experiments both by hand and also doing some computer experimentation, but not much. So computing or identifying these sets of frames seems to be a hard work. So far, it's a challenge, and it seems that it requires complex combinatorial analytic estimations that go beyond my toolbox, so to speak, at least now. Now, of course, it's possible that there may be a simple structural characterization of these families. It is conceivable, but I do not know of any. So if anyone wants to make a conjecture, give it a try, talk to me. Okay, so lastly, some conjectures and some open questions. Well, so first, to make it slightly easier, we may want to focus on the EMSO on just the two variable fragment of first order logic, which is already good enough to talk about, let's say, frames and graphs and all this. And even there, things are not much simpler, but at least I have conjectures towards which I have made some progress, which I want to mention. So the first conjecture is that the frame properties that are definable in existential MSO, in fact, this is on the two variable fragment, but I think it might actually hold in the general case, that are almost surely true in the finite. They are axiomatized, and I'll explain what I mean, by adding to the first order extension axioms all formulae that state existence of almost surely true kernel partitions of homomorphisms. That is the natural conjecture. So when I say axiomatized, I actually think that they can be derived in a suitable axiomatic system for MSO, for the existential MSO. But certainly, so the weaker claim is that they follow model theoretic logic. And likewise, for the frame properties that are definable in universal MSO, they are almost surely true in the finite. The claim is that they follow logically or axiomatically, deductively, by adding to the extension axioms all negations of formulae that state existence of almost surely false kernel partitions. Okay. And so, of course, there is a bunch of more questions to ask here, but I want to wrap it up and leave time for questions. So basically, what I want to say is that at the moment, this project is in a kind of, well, in a state where it is not clear how far it can get and how difficult it can get. So it's really, really challenging, and I welcome anyone who wants to join this challenge. So, yeah, one may want to ask questions. Yes, so this is a recent paper that I mentioned that has some more technical details. And lastly, one may want to ask a question, what possible applications could there be here? And so I can offer some speculations if you want to hear in the Q&A. But I'll end it here.